Hello, MAT223 students. Welcome to this video, which is application of diagonalization. In this video, we want to study one of the most important applications of diagonalization, and that's computing a general exponent of a matrix. So let's start with very simple example. We have a matrix. Uh, in this case, it's 2 by 2, but in general can be any square matrix, n by n. And we want the question is compute a general exponent of this matrix for n a natural number. Like for example, what is a to the exponent 1000? What is a to the exponent 100? What about 1 million? So, uh, as you know, computing the first few exponents, it's not hard to do directly by matrix multiplication. For example, if you want to get a squared, you just do a times a, which is 1210 times 1210, and then you do the matrix multiplication, which you get this times this, dot product that, you get 3, and then this dot product this, you get 2, this dot product this, you get 1, and this dot product that, you get 2. And if I want to compute a cubed, I need to do a times a squared and compute another matrix multiplication, which I don't do, but it's you can do it. But the point is, if it's a2, a3, it's just two matrix multiplication. But assume that we want to compute, for example, a1000. If you want to continue doing this until you get a to the exponent 1000, you need to repeat this process of the matrix multiplication basically 999 times. So you need to do 999 matrix multiplication, and that takes a lot of time. So it's not at all easy or obvious or trivial to compute large exponents of a. Or even worse than that, finding actually a formula for the exponent, a general exponent of n. It's not at all obvious or trivial question. But if you do diagonalization, it becomes very trivial. Let's first diagonalize this matrix and then we discuss the how do I use it to compute the nth exponent of a. So let's first focus on diagonalization of this. To diagonalize a matrix, I need eigenvalues and eigenvectors. So first, eigenvalues, I need characteristic polynomial. Characteristic polynomial of this, by definition, it's determinant x identity minus a. This matrix x identity minus a is first x identity, it's xx00 minus a, which is 1210, and you get this minus this, which is x minus 1, negative 2, negative 1, and x. Now determinant of this 2 by 2 matrix is this times that minus this. So it's x minus 1 minus this times this is 2, minus 2. If you expand, you get x squared minus x minus 2. And if you factor this polynomial, it's x minus 2, x plus 1. So to find eigenvalues, I find the roots of characteristic polynomial, which are two things, negative 1 and 2. So I have two eigenvalues. Already I know that the matrix is diagonalizable. Why? Because it's a 2 by 2 matrix having two different eigenvalues, and each eigenvalue has at least one eigenvector. So it is diagonalizable. But to do the computation for the exponent n, I need the actual diagonalization process. So I need to find the matrix P and D. So to do that, I need eigenvectors as well. So let me then compute eigenvector of this and eigenvector of this. So for first eigenvalue, to solve find eigenvectors of it, I need to solve system of equation that is eigenvalue -1 times identity minus a x equals 0. I need to solve this homogeneous system of equation. To find the eigenvectors of the eigenvalue lambda, I need to solve this homogeneous system of equation. The basic solutions for this homogeneous system are basic eigenvectors for that eigenvalue. Okay, let me solve it. This is the matrix. This is the matrix X identity minus A. Now I need to put -1 in this. X -1. If I put -1 in that is -2, -2, -1, -1. And the matrix X, which is the unknowns X, we have two of them, X1, X2. Okay, great. So basically the system of equation that I get is -2x1 minus 2x2 equals 0, -x1 minus x2 equals 0. These two equations are actually the same equation. One of them is twice the other one. So basically you can consider only one equation, and the solution for that is moving one of them variables to the other side and taking that variable to be free. So for example, moving x2 or x1 to the other side, let's say, then you get, or x2 to the other side, x2 equals minus x1, you get this equation, and you can get x1 free. So x1 is free, let's call it t, and then x2 is, let me write x1 first, and then x2 is minus x1, which is minus t. T is a free parameter. Then, if I write in the vector form x1, x2, it's t, the coefficients of t are 1, -1. So I find this as a basic eigenvector. So this, it's basic eigenvector for lambda 1 equals -1. I repeat this process for lambda 2. Let me do it here. Lambda 2 equals 2. The system of equation that I need to solve, it's the homogeneous system 2 identity minus ax equals 0. But 2 identity minus a is this matrix, except instead of x, I should write 2. So that becomes 2 minus 1, 1, and that just becomes 2. x1, x2 equals 0. So the system is x1 minus 2x2 equals 0, and x2 minus x2 plus 2x1 equals 0. Again, the two equations are negative of each other. Sorry, that was negative x1, x2, 2x2. The two equations are negative of each other. So basically, they are the same equations. You can consider only one of them and you bring that to the other side. You get x1 equals 2x2. So this time I take x2 to be free parameter. Let's say x2 equals t. Then x1 is 2t. So writing in the vector form, x1, x2 is t 2, 1. Hence, this is basic eigenvector for lambda 2 equals 2. So I'm done with the computation of eigenvalues and eigenvectors. Hence, I found the matrices that makes matrix A diagonalizable. What is it? We have A. If you remember the definition of diagonalizability, it's that there exists a matrix P invertible and a diagonal matrix D such that A is P D P inverse. And after finding eigenvalues and eigenvectors, basically I can write down what is the matrix P and D. The matrix P, it's putting the eigenvectors as columns of this matrix. So I found this as one eigenvector, 1, negative 1. I first write that as the first column. I found this as another eigenvector, and I will put that in the second column. And that's matrix P. Okay. Matrix D, it's the diagonal matrix in the same order of eigenvectors. Because I put this as the first column of P, this will be the first diagonal entry of D. So it's negative 1. Then, because this, it's in the second position of the column of D, P, this will be the second diagonal entry of D. So 2. And that's the diagonal matrix D, and P inverse of this. To compute P inverse, I use a 2 by 2 formula for inverse. It's 1 over determinant this, which is 1 plus 2, which is 3. So 1 over 3, basically. And then I need to swap these and multiply these by a negative sign. So you get 1, 1, swapping these ones still remain 1, 1, and multiplying these by a negative sign. So you get negative 2, 1. This is the inverse of this 2 by 2 matrix. Now, let's write this equation. Let's raise this equation to the exponent. And what was my whole question? This is end of diagonalization. So I found eigenvalues, eigenvectors, the matrix P and D, P inverse, and this equation is satisfied. So end of diagonalization. Now I want to use this information that I found from diagonalization to actually compute AN. That's my goal. So let's compute AN then. I need one more page for my computation. But for now, let me just compute AN. What is AN? It's this thing, A is this, to the exponent n. Now you see why diagonalization help you to compute this easily. And this is nothing other than multiplying this by itself n times. So it is P D P inverse times P D P inverse n times. And this whole thing is n times. But note that P and P inverse are inverse of each other. So when you multiply by each other, they become identity, or basically they cancel each other in a multiplication. So this also cancel the next P. This P cancel with P inverse before it. And basically all of them cancel. What do you get? You get P, D, D, D. How many times? N times. N times D. And then P inverse. This last P inverse and the first P does not cancel, which is P dn P inverse. So basically, if you want to raise this to the exponent n, you can just raise the middle part of it to the exponent n. But middle part of it, it's a diagonal matrix. Raising a diagonal matrix to the exponent n, it's very easy. This to the exponent n is just raising the diagonal entries in to the exponent n because it's diagonal. So now I can find AN. I found that AN is P dn P inverse by this computation here. Now I replace things. P is this. dn, as I mentioned, is this to the exponent n. Because it's diagonal, it's just diagonal entries to the exponent n. And P inverse is this matrix. Okay, now let me compute this. Let's do this matrix multiplication, bring this one over 3 out, and do this matrix multiplication. What do we get? We get this times this, which is just negative 1 to the exponent n. Then this times this, which is 2 times this, which is 2 to the exponent n plus 1. Then this times this, which is negative 1 times this, which is in total negative 1 to the exponent n plus 1. And finally, this times this, which is 1 times that, which is 2n. Now I need to also multiply it by 1, negative 2, 1, 1. So you have 1 over 3. And this times this, which is basically sum of these. Let me write 2 to the exponent first, and then plus negative 1n. Then this times this. What is it? It's this times this, which is basically negative sign combined with this. You get negative 1 to the exponent n plus 1, and then multiplied by 2. Multiplied by 2. Or if you like, write 2 before. Then this times this, which is 2n plus 1. Let me always write 2 term first and that second, or the other way, but let's be consistent. So let me write this after and this before. Then this times this, which is negative 1 to the exponent n plus 1 plus 2n. And then this times this, it's again a negative sign added, multiplied by this, you get negative 1 to the exponent n plus 2, but that's the same as negative 1 to the exponent n, because two negative signs multiplied by each other, it's just cancel each other. And times 2, because this times this, it has also 2. And finally, this times this, which is plus 2 to the exponent n. And basically, I found a formula for an. Let me highlight this. This is the formula for an. Look, with only doing two matrix multiplication, I computed something that in general, for example, needed n minus 1 matrix multiplication. For example, if you want to compute a 1 million, you need almost 1 million matrix multiplication if you want to do it directly. But now I can just replace 1 million in this as n, and I have the computation. See how like non-trivial it is. So that's the advantage of diagonalization. Diagonal matrix, has very nice properties. In particular, exponent of it is very easy to compute. This process of diagonalization allows us to take advantage of this simple property of diagonal matrix, that exponent of it is easy to compute the exponent of a general matrix which is not actually diagonal, but it is diagonalizable. So this is one of the very important applications of diagonalization. If you diagonalize a matrix, basically you can find an explicit formula for an. That's the idea. Now let me use this application in another problem. Consider this problem, which at first it doesn't look at all related to linear algebra and our course. We have a recursive sequence which is defined by it's given two first terms, A0 is 0, A1 is 1, and then every next term is defined in terms of two previous terms. Okay? This defines the sequence. For example, let's compute first few terms. A0 is 0. Then A1 is 1. That these two are given to me. Okay? Look how I proceed in this computation of sequence. I look at these two entries because I want to do next term. Next term, it's the one that I want to compute. To compute this term, it depends on the previous two terms. So I reserve this in my memory. And then when I want to compute next term, I use this in this formula and I compute the next term. So this becomes twice the, no, this plus twice this. So A2 becomes 1 plus twice 0, which is just 1. Now, to compute the next term, I don't need this term anymore. I need the previous two terms. So what I do is I erase this from my memory. Now in my memory, I have these two terms. And I use this to compute the next term. So A3. What is A3? It's this plus twice this, which is 1 plus 2, which is 3. Now to compute the next term, I don't need this anymore. I need these two terms. So I keep these two terms in my memory. And then I find this. And so on. So now let's assume that you want to compute what is A1 million. Or in general, what is a formula for AN which is not recursive, it's explicit formula. So it's not at all trivial or obvious that how you should find a formula for AN in general. Or if you want to do this directly, that takes a lot of time. If you want to continue this process almost 1 million times. So it's not at all trivial. But let's find a mechanism that I can compute the AN in general. So let's first under model do a mathematical model of this process that I explained to you. Having two things in my memory, compute the next thing and erase one of the things from your memory and take the new thing in your memory and move forward this process. What is the process? Basically, let me again start from the beginning. So I started with A0 and A1 in my memory. So I have two things. Then I do a process, I compute A2, and the result is that I erase A0 from my memory and I keep A1 and A2 in my memory. So basically, I'm talking about a map, about a function that takes two things, A1 and A0, at the beginning in your memory. These are in your memory. And what it returns, the function, returns A1 and A2 as the result. Erase this from the memory and replace it with this, basically. So it maps it to A2, A1. This is just the first step. In general step, you have A n minus 1, a n minus 2. If you are at some place, you are looking at two things, let's say a n minus 1, a n minus 2. Then you compute next term, which is a n using this formula, and then erase a n minus 2 from your memory. So you are at some point, you are you have a n minus 1 and a n minus 2 in your memory. Then next step is to compute an using these two, then erase this from your memory and take this in your memory. Then the result is an and an minus. So this is this process. Now let me find a formula for this map. This is a map from R2 to R2. Let me find a formula for it. Using these formulas that I have, what can I write? Let me first do it for this, but then I do it for this. I know that A2, it's given in terms of A0 and A1 using this. So A2, it's A1 plus 2A0. And I recognize this. This is actually a linear map, and the corresponding matrix of it is the coefficients of A1s and coefficients of A0, which is coefficients of A1 is 1, 1, coefficients of A0 is 2, 0, and then I have A1, A0. If you don't believe it, check it. This matrix multiplication, if I do this matrix multiplication, the result is this. This times this, that's A1 plus 2A0. And this dot product this, it's A1. So actually the map is a linear map, which is given by this matrix. Let me give a name to this matrix, A. Then to find a general formula for a general step, it's the same process, an, it's given by this. So it's an minus 1 plus 2an minus 2. And this is the same coefficients. Coefficients of an is an minus 1, it's 1, 1. Coefficients of an minus 2, it's 2, 0. So that's the same matrix as A. Because I'm doing the same step, no matter from step 1, 2 to step 3, or from step n minus 1, n minus 2 to a step n. Okay, then let's discuss what is actually doing this step many times forward. What happens to it? So I understood that this process, moving one step forward in the sequence, it's basically this linear map. It's applying this matrix multiplication, basically. Now, let me do a chain of steps, not only taking one step forward, but taking one step forward, two step forward, 3, 4, 5, in general, n step forward. So I start with A1, A0. That's my starting point. Always I start with these base cases that I have. Then if I do one step forward, I get A1, A2, A1. And what is this step forward? I found a formula for it. It's multiplying by matrix A from left. It's multiply by matrix A from left. Multiply this by left to A. Then you get this. If you do repeat this step, multiply by matrix A from left. Then you get A3, A2. And continue doing this. Multiply by matrix A from left, multiply by matrix A from left. In total, do this process n times. In other words, take n step forward. What do you get? You started with A0 here. One step forward, you get A1. Two step forward, you get A2. If you do n step forward, you get an. And similarly, you started with A1. One step forward, A2, A3. And if you do n step forward, you get A1 plus n. Or in other words, an plus 1. So basically, I found the formula. I found that an plus 1, an is start with this A1, A0 and take n step forward. In other words, multiply by a n times from left. This is multiplying them by matrix A n times. But that's nothing other than exponent A to the exponent n. Now you see the connection. Now, if you like actually to find a formula for this recursive sequence, or finding an in general or a 1 million, basically the question is the same as how do you compute a general exponent of a matrix? And that's exactly what diagonalization helped me to compute. I have the answer. If you look at this matrix A, it's the same matrix as this, which I already did, found nth exponent of it. Let me just bring this result there. Using diagonalization, eigenvalues, eigenvectors, I found the nth exponent of this matrix. Now I can use it in this question. So basically, I can say that this is an. A n plus 1, I'm writing this. A n plus 1, a n equals. This is a n, I replace it here. And this is a1 and a0, I have them. A0, it's 0, a1 is 1. 1, 0. And I just need to do this simple matrix multiplication, and not even all of it. What do I want to find? I want to find a formula for a n in general. If I look at here, a n is actually the second entry of this matrix. So I don't need to compute this. While it's very simple to compute, basically I only need to compute this. But this is just 0, so it's very simple calculation, and you get basically only the first column of this matrix. So let me just copy it. But what I'm looking for is a n, which is this entry. Note that that's also a match with the other one. If you like, this is the same as I mentioned, a n plus 2, which is basically this one more. So it matched that. If you read a n from this or a n plus 1 from this, they are consistent formulas. Okay, then what I wanted was a n, which is the second entry of this matrix. So I found a formula for a n, which is 2n plus negative 1n plus 1 divide 3. Look, we found a very non-trivial equation using a sequence is a recursive sequence is defined like this, and you want to find the formula for an. It's not at all obvious what we should get, but it has this simple formula. And now let me answer for the last thing, the original question. What is a 1 million? If you wanted to do it directly, good luck. It takes forever. If you want to directly compute a 1 million by doing any term with some of the previous two terms. No, by this formula. But now it's very simple. A 1 million, if you like, it's just 2 to the exponent 1 million. Negative 1 to the exponent 1 million and 1, but that's odd number, so it's just negative 1 over 3. That's as simple as this to compute a 1 million, while again it takes forever for you to directly compute it. See how powerful, how useful this diagonalization is. It has many applications all over the mathematics, in particular solving differential equations, system of differential equations, and so on. And a lot of applications in computer science, machine learning, and everything. I hope that you enjoyed this video, and thank you for watching.